yeah, as Frank said, I'm happy to be presenting reducing risk and uncertainty in offshore engineering with 3D seismic reflection data. So here we go. I felt that with the topic today and not really fully knowing the audience that would join, that it would be good to not only introduce myself and what we do at AtkinsRéalis, but also explore a bit more about marine geophysics specific to offshore engineering. So just looking at a couple of different techniques before we then get down to looking at specifically perhaps the topic of the title, which is looking at 3D seismic methodology versus a 2D seismic methodology with a case study from the Baltic, which I've called Baltic Offshore Wind Farm. It's yeah, we've got permission to share the data, but not specifics about the project. So happy to introduce myself. I'm Ed Henden, as said, a principal marine geophysicist, and I've been working with AtkinsRéalis, formerly Atkins, since January 2022. And before that, I worked in seismic processing as a geophysicist for 12 years, and originally that was with TGS in Bedford, where I currently live. And then I spent 4 years in Australia, initially with TGS, and then a year with Down Under Geosolutions, or known as DUG, that some of you may be familiar with, before coming back to the UK to rejoin TGS until joining Atkins. But before that, in my early career, so I graduated from Southampton University in 2006. And swiftly went to EMU Limited, a marine survey company based just down the road from there, now part of Fugro UK. So yeah, I worked with them for 4 years before going into seismic processing. So at AtkinsRéalis, we're involved in our marine geoscience team. We're involved in all parts of the development process for offshore structures, including for offshore wind. So through from studies at a concept stage, through the site investigations, we support with survey management, survey design, and then reviewing the data, interpretation and integration, both on the geophysics and geotech side, so that we can understand the ground conditions, which leads us into what we're talking about today. And then, yeah, all sorts of different aspects of the design as well, which is not my cup of tea, but yeah, perhaps we'll see a bit more later on. So yeah, in terms of our industry for offshore engineering, we have various standards and guidance, but the main ones are the ISO 19901-10, which is originally from the petroleum natural gas industries, specific requirements for offshore structures, and Part 10 is the marine geophysical investigations. There is a Part 8, which is the geotechnical side as well, which is of interest to anyone who might want to do some further reading. But more recently, we have the guidance from OSIG, which really do form what we consider the basis for offshore site investigations, for specifically for offshore renewable energy developments, but also covering other offshore engineering projects. So just a bit more on that particular guidance. I would highly recommend having a look at that one, because yeah, this covers both geophysical and geotechnical surveys. It was first compiled in 2014, before which there wasn't really any guidance, and yeah, contractors just did what they wanted. But yeah, with the developing offshore wind industry, that these have been put in place by the Society of Underwater Technology Offshore Site Investigation and Geotechnics Committee, and revised in 2022, which was quite a significant revision. But yeah, a key quote from that one is, some of the more significant risks that the developers of such projects face are the hazards and uncertainties that ground conditions present to project development, design, construction, and operation. The primary sources of information that are used to minimize and mitigate the risks posed by ground conditions and geohazards are complementary geophysical and geotechnical methods. So really just highlighting that it's not one or the other, it's really both in combination, and that's what we're talking about today. So looking at specifically the marine geophysics, this is the non-intrusive aspect of ground investigations, and they're really essential for managing that geological and geotechnical risk within the ground investigation phase. The benefits of geophysics are that they that there's a wide range of data which we'll look at, and they can be acquired simultaneously from one vessel, and we can cover large areas in a relatively short space of time, and they provide continuity and correlation between the geotechnical samples that we might collect. And there's also a range of depth of subseabed investigation due to the range of systems with the different sound frequencies. So there are limitations, and perhaps with Giuseppe's talk today as well, this touches on this. So on its own, geophysical data is a qualitative result. It does require ground truthing with geotechnical data. They are very sensitive to weather and noise, and geophysical data can be negatively impacted by ground conditions such as presence of shallow gas, which can obscure the signal in the subsurface or scatter the energy, or other complex ground conditions as well. So we're looking in the ground investigation flow chart. We've got various phases of geophysical survey, often a reconnaissance stage, which might look at a larger area, and then as you go through this flow, collecting geotechnical data and integrating that, producing a ground model, you may discover more risks that you didn't know about that you may then need to go and collect more geophysics for. So the case study will give an example of that sort of flow. So marine geophysical survey systems can be broken down into seabed systems, which measure water depth and seafloor topography, also known as the bathymetry. We can look at the seabed sediments and the creatures that live on those and in those habitats on the seabed, and then also looking at obstructions. And then subseabed, looking at the shallow and deep geology, and looking at obstructions which may exist beneath the seabed. So an important question to ask is, how deep are we looking? This can vary across offshore engineering projects. So cable installations may be only looking down to sort of 3 meters below seabed. Floating wind may be looking down to 20 meters. Fixed wind foundations could be down to 70 meters, while underground energy storage or oil and gas exploration could be looking several kilometers. So we really need to tailor our geophysical surveys to target those depths of interest. So looking at the seabed surveys, we have multi-beam echo sounder, or MBES, and this typically vessel mounted and combined with sensors to account for the vessel motion. And a single swath of data can be collected in one pass, and that will map out the water depths and the seafloor topography, and perhaps image the obstructions that are on the seabed as well. So from that, we'll get a datum corrected digital terrain model, and we can compare different bathymetry data sets over time to get an understanding of potential sediment mobility. And we can also look at the acoustic backscatter intensity from the multi-beam to understand what the seabed sediments might be. But really, that goes hand in hand with the side scan sonar, which is the primary sensor for detecting seabed obstructions, such as wrecks and debris on the seabed. And again, the variation in the reflectivity can indicate changes in the sediments on the seabed, and used in combination with the backscatter data. And again, you can see features of mobility indicated by the presence of bed forms such as sand waves or ripples. And also the importance of the environmental surveys for consenting purposes in offshore developments. And benthic sampling would be the ground truthing method for ground truthing features identified in the side scan sonar data outputs. But looking subseabed, we have these different types of systems, and certainly this isn't an exhaustive list, but if we're looking, if we've got a depth of interest at say several hundred meters, then we might be looking at air guns as our seismic source. If we're looking down to maybe 100 meters, then what we call ultra high or extremely high, and the jury's out with deciding on the definitions with those wordings. So I've been using ultra high in this presentation. We could talk about that later perhaps. And then if we're looking really shallow in the subsurface, so top few meters, then a sub-bottom profiler such as the Innomar system is ideal for that. And here's just some data examples showing us air gun data down to about 300 meters, some Sparker data down to about 80 meters below seabed, and then sub-bottom profiler. And yeah, the resolution, vertical resolution of these is significantly different. So we have centimeters to a few meters for airgun. So I just want to touch on 2D versus 3D. So 2D UHRS, ultra high resolution seismic, typically a single seismic source such as a sparker, and then a single multi-channel cable. So it might have up to, say, 96 channels along a cable, which could be 100 meters long. And this would be acquired along a grid of lines, typically, say, 50 to a 200 meter line spacing, and then cross lines in order to tie the seismic together at 500 to, say, 2 kilometer spacing. So we can cover huge areas with this. However, the outputs tend to be quite low resolution because you're having to interpolate between those lines and across what we consider data coverage gaps between the lines where there's greater uncertainty. Think of this as like a 2D ultrasound. You can see that there's a baby there, but you can't really pick out any details or any emotion in the image. However, for 3D seismic or 3D ultra high resolution seismic, we have multiple sources and multiple cables, and this has really been developed or scaled down from oil and gas exploration methods. So in this case, we've got 4 sparkers and 4 cables, but you could have up to 10 cables or possibly more with larger vessels. And here you're getting full coverage across the swath of data that's collected, and there's no data coverage gaps. And it's, yeah, tends to be very high resolution. You can create a volume 3D cube, which can be cut and interrogated in lots of different ways. And ultimately, we're trying to get full coverage over, in this case, a wind turbine location within a corridor of 120 meters. So yeah, the equivalent in ultrasound would be this sort of 3D image of a baby's face, where you can actually start to see a baby smile. You can see the nose and different features, much more higher resolution. So I just want to take you on a bit of a journey with this case study from the Baltic Sea, which we've been working on over the last few years. So we've been supporting since 2022, including oversight of the ground modeling, both shallow and deep, across the array area and the export cable route. And it's involved data review, reprocessing and reinterpretation across the different campaigns, so 2023 and 2025 in particular. But in 2020, the developer collected this fairly sparse 2D ultra high resolution survey with multi-beam, side scan and sub-bottom profiler along a grid of lines. It was a very large area, 185 square kilometers. And when we reviewed it in 2022, we identified that the original seismic processing was not sufficient. So we proposed reprocessing for this, which greatly improved the interpretability and helped develop the shallow and deep ground models for that location. So that helped them develop a grid of wind turbine generators, originally proposed to be about 6 to 7 WTGs. So in 2023, they did a more focused survey along these corridors, about 1.2 kilometer spacing corridors. And within each corridor, they collected 5 lines at 25 meter spacing. So it sounds like it's much higher resolution, but it is only focused along those lines. So between those corridors, you do have gaps of about 1 kilometer of lower confidence. However, that allowed them to be able to plan their final layout. So they developed their final layout of around 40 WTGs and their offshore substation. And then in 2025, we supported them with acquiring a 3D UHRS along corridors. So again, 120 meter corridors in lines of the WTG locations. And I'll explain a bit more why they did that. So in 2024, after the 2023 survey, we were focusing on the top 6 meters for a shallow ground model. And we identified in the sub-bottom profiler and also in the multi-channel UHRS 2D profiles, there were certain features which appeared like channel features. But then when we were picking them, we noticed that it wasn't possible to interpret them across lines. even though we had 25-meter line spacing on the corridor lines. This led to low confidence geohazard interpretations and certain residual risk in the areas of low coverage between the corridors. And these features hadn't been targeted by the 2023 geotechnical sampling campaign, and therefore it wasn't understood what their geotechnical parameters might be. So a further geophysical and geotechnical campaign was recommended to target those features particularly, to understand the geohazards. And yeah, the recommendation was to use 3D. So in 2025, the developer commissioned a 3D seismic survey to investigate these features along the offshore structure corridors. And that would help with micrositing the wind turbine generator foundations and also support the installation of those structures, including jack-up leg penetration. So within the extents of those corridors, we achieved full coverage with a very high spatial resolution of 0.5 meter bins, 3D bins, and that allowed imaging of these features. And we actually were able to identify features such as suspected kettle holes and iceberg scours and other glacial features, which actually may be quite spatially limited. So in this case, this is less than 25 meters across, and therefore that's why it was only seen on one geophysical line on the 2D survey, but on the 3D you can map it. You can map its extent very, very accurately. And yeah, some nice examples of other features which potential geohazards to avoid during construction. Another objective of that survey was to detect subseabed boulders because these pose significant risk to monopile installation. So some of these boulders can be upwards of 3 meters in diameter and typically a much denser material than the clay that it's emplaced in. So it could be a granite boulder or something else. But yeah, certainly if you hit that with a monopile foundation, it can cause buckling or other problems, or even for the jack-up leg, it can cause capsizing. So yeah, we were successfully able to image and interpret and map these subsurface potential boulders, often called point diffractors, because we can't confirm or deny the presence of a boulder without fully investigating. But these are just some of the outputs from that survey. So yeah, in terms of recommended reading, I'd certainly recommend, if you are interested in this, to read this paper that was presented at the ISFOG conference last year by Vicky Catterall from RWE. And really, there are various developers that are moving away from this multi-year campaigns with lots of different acquisitions and looking to do one single 3D seismic acquisition once at the beginning of the project, and then you don't have to then repeat it later or go in and do anything again. So yeah, it's an interesting read, but very appropriate for this topic. So I think that's it for today in terms of my presentation. So I'm happy to hand over back to the conveners, and then we'll take any questions later.